Okay, today we're gonna revisit our bolted joint that we did in SolidWorks. There's also a video on Moodle of solving this one by hand. The thing we're gonna do different this time is that instead of a static 20,000 20 kilonewton load here, we're gonna make this a repeated load. It's gonna go from 0 to 20 kilonewtons repeating. So it'll have fatigue that we have to worry about on these bolts. And so we'll look through how to do this. You still, even when you have a fatigue scenario like this, you still do need to check on the yielding for these bolts, just like we did with either the SolidWorks analysis or by hand. Those gave us factors of safety of, let's see, when you do this by hand, we had a factor of safety of 1.29 more or less, and then by simulation we use SolidWorks, you got a 1.31. so they're pretty much in agreement that somewhere around 1.3 is your factor of safety against yielding. Remember, these bolts, they don't have a very large plastic region. They're not brittle, but they do look more brittle than regular steel would be. So we do have relatively low factors of safety against yielding because we're also preloading these. This diagram doesn't show it, but we're preloading these to be reused. And so that gives them 75% of what's called their proof strength. We're going to generate that much stress, axial stress, in these bolts as we load them up the very first time when we install them. So they're already close to yielding, and then we have a little bit of factor of safety on top of that. So what we're going to do today is look at this same setup, the same M10 by 1.5. So this is 10 millimeter bolts with a distance of 1.5 millimeters between the threads. They're single start, so there's only a single thread on these bolts. We're going to look at them in two different fashions. One where the threads on these bolts are rolled. So what that means is that when the threads are formed, instead of putting it on a lathe and cutting away material, you're actually forming the threads onto the existing material. So you're squishing the material around to form the threads. So they're rolled. So that does a couple of things. For one, you don't have machining marks, so you don't have this some little scratches and everything, and it work hardens the bolt material. So most fasteners, particularly higher end fasteners, are going to have rolled threads, but cheaper fasteners and just other fasteners are going to have cut threads. And so we're going to look at, if these have rolled threads, what is our factor of safety against fatigue? And then we're going to do the same analysis again, but if they have cut threads. This is a little bit different process that we're going to need to go through if they have cut threads. So we'll do that, and we'll be over here. Most of this is in chapter, well, actually, I guess all of it is in chapter 811, but there are some tables and charts that are outside of that exact chapter. They're scattered in chapter 8. If you had bolts that were of a different material, then maybe you would need to go way back into the back of the book and get some material properties there. These, the bolt strengths and everything that we need, will be in the chapter 8. Dimensions on these bolts we already have, so we're going to reuse a lot of the same things that we used when we looked at this from a static analysis, like the C, the joint stiffness constant, on how much. In fact, let's go ahead and write that down. So C, get that out of the way, is the joint stiffness constant. And for this scenario, now this one was not so bad. Remember, that's where you go in and calculate these frustum and figure out basically the spring rate of your joint here. And the idea is that you're trying to figure out how much of the external load is your bolt carrying, and how much of the external load are all the members being compressed carried. And so for this scenario, it came out to be 0.2075. So a little over 20% of any external load gets shifted over to the bolts, and the other 80% or so is carried by the members. So it's releasing the built up compression in the members first, or well, 80 to 20. So we'll need that to calculate a few of these things. Basically, we need to know how much of this 20,000 newtons is going to the bolts. We do have 4 bolts, so the 20,000 newtons we're going to assume that this is a symmetric pattern, and there's no reason why one bolt is going to carry more of this 20,000 than the others. So we're going to divide it up equally. So each bolt is going to have to carry their portion of 20,000 divided by 5 newtons, 4. So it'll be 5 kilonewtons. So what was special about this one is, normally you have to use all these individual little pieces, but here, this is all steel, and there's no washers either that are made of any different material. It's just the bolt head and the nut on the other side that we can't see. And so since it's all the same material that is in the grip, then there's a little bit simpler equation that you can use to calculate the member stiffness, which you use to calculate joint stiffness. The bolt stiffness is no different than you calculated it the other time. Okay, so let's start on all the stuff we need to figure out. So over in your book, you've got a couple of charts. We'll get to these later on. This is the stress concentration factors. We're going to use these as strength reducers, but this is for cut threads. So if you have cut threads, what they're actually talking about here is, here's rolled threads, and you kind of see how the cut threads have a higher stress concentration factor than rolled threads. They have it divided into 2 different categories, one for the lower grade bolts and one for the higher grade bolts. So you do have to make sure you're in the right column for SAE or metric. They have fillet. So these are 3 different common failure points. Well, I guess 2 here. These are threads, and this is the under the bolt head. So you can kind of see here, your book points out 3 different common places where most of the failures that do happen are going to be right where the nut and ends and the joint begins. So on our example, it would be right under there. Right under there is where most failures happen, 65% of the time. 20% of the time it says at the end of the thread. That doesn't mean down here. It means where the thread ends on the bolt. So there's this region called runout where you have stopped making the threads, and the rest of the bolt is the shank, the unthreaded portion. So that transition between threaded and unthreaded is the 20% they're talking about here. Sometimes you'll hear this called as at the runout, where you basically kind of remove the lathe tool when you're making the threads, and so you gradually do that so that it's not an abrupt end to the threads. They run out gradually. And then 15% of the time under the head, so that's meaning under the bolt head, and that's cover that up, under the bolt head over here. So under the bolt head, somewhere in the middle where the runout is, and most of the time it's actually right in there. Let's see, what else do they give us? This table is if you have, so this is over here, it even tells you with rolled threads. So this table will only give us values for rolled threads, and it gives us some of the grades for SAE and some metric grades, and then some different bolt sizes that are typical in those thread classes. This is your endurance strength, fully corrected endurance strength that you can use SE without having to go in and calculate a fully corrected endurance strength. So if you have rolled threads, of a certain grade that fit into a certain size range, you just go find your endurance strength from a chart like this. So this is table 817. If you don't have rolled threads, you have cut threads, then you have to go back over here, use a KF. This is not necessarily the same KF that is the lowercase kf that goes into the fully correcting the endurance thing. We're going to use this a little bit differently. We're going to use this instead of a stress riser. We're going to have it as a strength reducer at the end, because instead of multiplying something by 2.8, we're going to divide by 2.8 or 3.8, whichever we need. They have a couple of simple equations for alternating stress and mid-range stress, and we'll need those to build our chart. I actually do go in later and build the diagram so we can look at it, but you don't have to draw the picture. We're going to use Goodman and build that diagram with alternating mid-range stress here. So you can see a lot of the same terms that we've already used. There's C, the joint stiffness. P max and P min for us, that's the external force, the maximum external force, and the minimum. So most of the time bolts are under repeated loading, where they go from 0 to some maximum, which is what we have in our setup. Over here, we're going from 0 to 20,000. And that's pretty typical for bolts that are in a tensile setting. It's not necessarily true. You don't have to go all the way to 0. Maybe it goes from 5 to 20 or whatever. So that would change up a little bit of what we're going to do later on, but we're going to just go from 0 to 20,000. That's relatively common. And so we'll be able to use these two, 835 and 836, to calculate the alternating and mid-range stress. We'll build us a diagram similar to this for our scenario, and we'll put Goodman on here, the modified Goodman. There's just where your book does say that bolts are often in a repeating load situation where it goes from 0 to some maximum. So you do have to pay attention in your book that there are some equations that are listed that are specific to this scenario. So they do make some assumptions that these equations are only good when you do have 0 to some max. Let's see if I can find. Yeah, here we go. So over here, this is on page 439. So they have your failure, for Goodman, Gerber, and ASME elliptic. They have these solved, but you do have to make sure that you're under a repeated load scenario. Otherwise, you do have to go back and not use these, use the more general equations. So you do have to be careful that you can't blindly use one of these equations thinking that you're doing the right thing, but you don't have repeated loading. So you don't go from 0 to some maximum. So these equations are only good if you have that scenario. Okay. Let's see, what else do we need? Let's see what else we have over here. Well, there's those equations again. Again, the ones that are only good for repeated loading. And then this is a reminder that you do need to go back and check yielding. So we've already done the yielding check when we did the static analysis. So this is like the first cycle yielding, making sure that you don't ever get to a fatigue situation because it yields before you ever get there. So we were okay on the first cycle yielding. We had a 1.3-ish factor of safety. Okay, let us start calculating some of these things that we need. All right, so first, might as well do the alternating stress. All right, so get my notes. The equation, this was equation 835 on page 437, and it said sigma A is C times P max minus P min. So P is the external load. This is a parentheses, not another C. And then we divide that by 2 to get the amplitude instead of half the amplitude, to get our alternating stress. How much is it going from above and below the mid-range? And then AT is our tensile area of the bolts. We also got that last time from the back of the book, actually. Actually that's on table. AT is on table 8.1 on page 404. So it's just earlier in chapter 8. And for us, it was 58 millimeters squared. So that was for the bolts that we were using, the M10 by 1.5. So you just look that number up in a chart. So when we plug in our numbers, C, that was the 0.2075. P max is 20 kilonewtons. P min 0 kilonewtons, so we're going all the way down to 0. 2, and then area of our threads 58 millimeters squared. We solved this. Oh, you know what? We already have a slight error here. This 20,000 is the total external load. We have 4 bolts, so each bolt only has to deal with 5,000 of these kilonewtons, or 5,000 newtons. All right, so we're going to divide 20 by 4 and assume that each bolt is carrying an equal share. So 5 kilonewtons per bolt. So that gives us a value of 8.94 megapascals. All right, let's get rid of that 20. Maybe we could go ahead and do our mid-range. So this is right under this one, equation 836 on the same page. So the mean or mid-range looks very similar. You still have the portion that only the bolt is carrying. P max plus P min, so we're going to actually average this one over 2 times AT. So that's the exact same, except we're adding instead of subtracting. But the bolt also has a preload on it, so we do have to add that guy in. So F sub I, that's the preload, but we're doing stress here, not force. So we need to create a stress by doing the preload divided by that tensile area to get the stress that corresponds to the preload. F sub I, if you remember that one, it was 28,275 newtons. How that got to be is that we said that we were going to use reusable bolts. So remember, there's 2 options: reusable and permanent, or at least non-reusable. The reusable, you load them to 75% of whatever their proof load is. If they're non-reusable, you load them all the way to 90%. So these are reusable with the 75% there. That proof load is equal to the proof strength, which is a number we get from a chart, times that tensile area. And so for us, the proof strength, now these are class 9.8, so that's where we'll find their strength. And that strength is 650 megapascals times the same tensile area as before, 58 millimeters squared. You got to make sure your units are working out here. And that gives us the, that actually would give us the proof force that we take 75% of and get 28,275 newtons for that preload. So that's the number that we put into SolidWorks when we were applying the preload to the bolts and axial force for a preload. But here we're actually doing stress, so we take that force divided by that tensile area to get the stress that corresponds to the preload. So we put these numbers in, C is still the 0.2075. Pmax per bolt is 5 kilonewtons. We still go down to 0 kilonewtons over 2 tensile area of the thread plus our preload. So the preload is going to dominate this number. We'll look at the individual components here in a second. Let's see, 28,275 newtons over 58 millimeters squared, or you could do 28.275 kilonewtons if you wanted to. So this number is actually the same as this one because we had 5 minus 0, 5 plus 0, so this is actually the same number for this part, 8.94 megapascals. And this number is much larger, 28,000 newtons divided by 58 millimeters squared gives us 487.5 megapascals. So our total mid-range, oh, we're off the screen. Let me move our page up. You can see those numbers. All right, so our total mid-range is 400, it's just the summation of these, 496.4 megapascals. So now we have our mid-range and our alternating stresses. So we could take these and go build our diagram if we wanted to and see where we're at on our load line. But before we do that, let's go ahead and put these numbers into the equation for Goodman. And Goodman's just the most conservative. You can obviously use whichever you feel is most appropriate. On any kind of exam or thing that I do, there'll be some indication, either something that specifically says use ASME elliptic, or that says use the most conservative equation, or whatever. You'll have an idea on, oh, I should use this one versus that one. So for us, we've done those. There was our alternating and mid-range. We did that. Here are, again, only for repeated loading. So we are in a repeating loading situation, so we can use this guy. So this will be the fatigue factor of safety according to Goodman. So I'm going to write that down, then I'll move this off the screen. So NF, this is for Goodman, is going to be SE, so our endurance limit, times our ultimate strength minus the stress associated with the preload, over the alternating stress, the ultimate strength, and then add the endurance limit. Let's get that off the screen. All right, so let's see these numbers. So actually we need to put that back on the screen because the very first thing is the endurance limit. And remember that we have a chart here that says as long as we have rolled threads, which is our first, right now we're in the rolled thread scenario. We'll do the cut threads in a second. So right now, rolled threads, ours were class 9.8. So that's the ISO here. Actually right where my cursor is, 9.8. M1.6 to M16. We're M10, so we're in that range, so this works. And it says that the fully corrected endurance limit for rolled thread bolts in that class range at that size, 140 megapascals. So SE for us is 140 megapascals. Let's see what else we need. We need SUT. So the ultimate strength, so that will have to go table 811, which I don't think I have a chart. We'll have to get the book out. So that's, what page is that on? 427. Here we go. So over here, Again, we have class 9.8, same size range that we fit into. There's our proof strength that we will use later on, or that we actually already used, I guess, previously. There's minimum tensile strength. That's the number that we need for SUT. It says minimum because these are a range. It is stochastic, statistically driven number. And so on the low end, you're at 90. Obviously, we're trying to be more conservative, so we're using the low end number. So not 90, 900 megapascals. So I got SUT as 900 megapascals. Sigma I, we actually just solved over here. We didn't call it that, but we solved it. So this preload over tensile area, that is the stress associated with the preload. So this term, the one that ended up 487.5 megapascals, that is sigma I. Sigma A we just solved, and that was the 8.94 megapascals. That was this number. So we need these, and we'll have our factor of safety according to Goodman. So 140 megapascals, 900 minus sigma I, 487.5 over sigma A, 8.94 times 900 again, plus our endurance limit, 140. Okay, we solve these numbers and we get 6.21. So much higher. Remember, our yield factor of safety was 1.3 when we did it by hand and by simulation. Fatigue looks like we're way under that. I did create these in Mathcad. So let's get our Mathcad window up. So I did go back and do a similar thing. There's C, the external load divided by 4 bolts, the minimum one, Fi. There's our sigma A and our mid-range. There's those values that we just found from the different charts. Here is the factor of safety that we just calculated, and here's our plots. So this solid red line, that's Goodman. This green dashed line, that is the load line. So you can kind of see where we start over here. I guess it's unfortunate where the blank part of the dash occurred, because it would have been nice that it actually showed the intersection here. But that's that 487 number megapascals. This dash dot line, the magenta one, that is the alternating stress, and then this one is the mid-range stress. So we're right here, and Goodman says we're going to fail way up here, and so that ratio from that distance to that distance is 6.21, and it even looks like this. This blue dotted line, that's our against the proof strength. That's not really what we're looking at right now, though. I just put it on there. But this is for fatigue, so not static loading. So the other thing that we said we were going to do is the one assumption we had in here was that these were rolled threads, and what that changed was, or what it gave us, didn't change anything, is that SE was a number we looked in the chart for. Now, we don't have a chart for if those threads are cut. So if they are cut, it's not as common of a scenario, but let's go ahead and see what that does. What we expect it to do is that it will make our situation worse, right? We should have a closer to failure scenario, because we've gone in, instead of forming these threads and work hardening the material there. We've cut material away and left all these machining marks. And you kind of got a sense of that over in this chart, where there are two side-by-side numbers, one for rolled threads, 2.2. Actually, we would be in this category because we're at metric grade 9.8, so we'd be down here. So 3.0 for rolled threads, 3.8 for cut threads. So this is a strength reducer by a factor of 3 for rolled and a factor of 3.8 for cut. So we expect that there will be a worse scenario when we have cut threads. So let's see, how do we put this 3.8? Do we just divide 6.21 by 3.8? What do we do with it? So here's what we're going to do. We're going to go back to chapter 6 basically and use those methods to figure out our cut thread scenario. So we'll still use Goodman just because we want to compare these numbers. So we'll still use Goodman. So this is for cut threads. Same, everything else is the same. So they're M10 by 1.5, all that's the same. But somehow we got one batch that's rolled and we have another batch that's cut threads. All right, so we use that table that we just looked at. That is table, if you didn't see the number, 816 on page 436. And it tells us that for our class of bolts, 9.8, that cut threads have a KF equal to 3.8. So this will be a strength reducer. You can apply these factors as stress risers or strength reducers. We're going to apply it as a strength reducer. Okay. So what we need to do is we need that SUT number again. So it has not changed. We're assuming it's the same material. We just, instead of rolling the threads, we cut them. So that'll give us SE prime equals SUT over 2. So 900 megapascals over 2 is 450 megapascals. Okay, so we have that. Then we go back to the chapter 6 to get our Ka, Kb, Kc, all the others, the temperatures, all those, we're going to leave at 1. But actually B, there's no size effect for axial, but so we have an axial load. We're assuming a pure axial load on here. Even though when we did our simulation, you could see that the bolts did want to have a bending moment kind of built on them. But we're assuming that this is primarily axial. So Ka, we have the equation there, A times SUT raised to the B. For our, remember this is the whole part of the point, is that these are machined surfaces now. And so we have the machined coefficients for here. It's where A is 4.51. And B is negative 0.265. And when we plug those numbers in, we have 4.51 times SUT is 900 megapascals raised to the negative 0.265. It's a relatively low factor, 0.7435 for Ka. Like I said, Kb, there's no factor, no size effect for axial loading, so we leave it at 1. Kc, the load factor for axial, there's a little chart that gives you, 3 options: axial, bending, and torsion. For axial, it's 0.85. Okay, and then all the others, like I said, temperature, all the environmental things, we're just going to keep those at 1. We have no information that they're anything different than that, so we're going to keep them at 1. So now we can calculate SE, the modified, fully corrected endurance limit will be this SE prime times KA. We'll put KB in there even though it's 1. KC, and then our KF here is being applied as a strength reducer. So we will divide this thing by KF, the whole term. So this is 450 megapascals. Ka was 0.7435. Kb was 1. Kc is 0.85. And then we divide it all by 3.8, which got covered up. There we go. When we do that, we get 74.84 megapascals. So this is compared to our, from the chart for the rolled threads, where it was 140 megapascals. Same thread, same bolt, other than instead of forming the threads, we cut the threads. We're at almost half of where we were on our endurance limit. At that point, we go back to this equation. So this is Goodman with rolled threads. And then we can do Goodman with cut threads. And instead of 140, we will have that 74.84 number. Ultimate strength didn't change, it's still 900. Minus the stress associated with the preload does not change. We haven't changed our amount of preload. What do we have here? Our axial stress didn't, or not axial, our alternating stress still going at 8.94. 900 megapascals is still there. Plus our endurance limit did change. It went from 140 before to 74.84. This new number for Goodman cut threads is 3.541. So it still says that we're not in danger of fatigue failure in this scenario, but it is worse to have cut threads than rolled threads. But the real danger, well, not danger, but the real thing we have to look at first is the static, which said we had a factor of safety equal to 1.3, more or less. 1.298 and 1.31 or something, depending on how we did it. You can also, like I said earlier, you can see these, if you do draw the actual diagrams, you can see basically, since our load line is a slope of unity, then what you could do here, if you are working over in Mathcad or something similar, I guess Excel could do the same thing, it's just plotting straight lines. So Goodman is a linear line, but the others, you know, they have some curve to them, so you do have to plot something different. But if you're in something like, now this is Mathcad 15, so it's the older version. It's still available, but it's the one that I know how to use better. There is a parallel product, Mathcad Prime, that can do the similar things. I just don't know all the buttons to push to make it do what I want it to do. So I know how this one works, so I use it. So if I right click here, I can trace, and let's trace on our Goodman line to where, whoops, wow, we're scattering around everywhere. Let's just click then, let's not trace with the, normally you can move the cursors, but it's messing with my screen. So I have a Y value here at this intercept of 55.378. Lost my pen. Let's put it over here. 55.378. And then I have a Y value here, right there, where my load actually is of 8.94. That number should look familiar. And if I divide those, 55.378 divided by 8.94, I get that 6.2 that we had when we solved the equations directly. So those equations are solving this intercept. Now, what I just did with the y value is it works because my load line is a slope of 1. If your load line was not a slope of 1, well, first you wouldn't have the same kind of loading that we have, but then you couldn't just do that. What you actually have to do is find the length of wherever this thing intercepts down here to this intercept, so that whole length divided by the other length. So the actual load scenario down to here. So you have to have that ratio. Since the slope is 1, then I can just take the y coordinates. If I could ever click on them. There they go. So the y value. Oh, it doesn't show you the actual thing. It only shows, or well, so what on my screen, I get to see this point in the XY coordinate. So that's where I got the 55.38. I didn't just estimate over here. It actually, when you're looking at the full Mathcad, it shows you that value. Not, you don't have to guess it. But it's a separate pop-up window that it's right here. Just can't see it. So our graphs do correspond with what the equations are telling us, which it should. The equations are basically just solving the intersection points on the graph. Okay, so that'll give us fatigue of bolts in an axial loading scenario. We have one more bolt thing. We have shear loading. So a lot of times bolts will be in shear, maybe even more often than they are in an axial load setting. So next time we'll look at that, and then we'll move on to other things, welds and so forth. I think welds are next. But anyway, that's all that we need to do for today. Hope if you have any questions, let me know, and we'll see if we can get those answered.